slope-intercept form. So if there was one equation, or certainly at least in the top 3 equations that I would want you to pull from the class and understand what it means, it's this guy. Y equals mx plus b. Very simple as far as just a couple of letters, but very, very, very valuable as far as a concept throughout mathematics. So to get behind what it means, m is slope. We've talked about that. We've seen that before. B is our y-intercept. We've also mentioned that y-intercepts are a point. So if we're actually talking about the intercept, it's 0, b. But you also may have noticed that anytime we talk about a y-intercept, the x is already 0. So that's why you only see the b in the equation. The rest is going to be your y and your x. That's what makes the equation. So usually when we're talking about the equation, we're not going to have a y or an x filled out. We can kind of insert things into it, but the equation should have m and b in order for it to be an equation of a line. Let's say we have an equation right here. Y is equal to negative 2x plus 3. We want to identify the slope and y-intercept. Well, pulling that from the equation above, the thing that's always next to our x is our slope, so m is negative 2. The remaining thing, or the constant, is our intercept. But again, if it's a y-intercept, we're talking about the point. So it's not just 3, it's a 0, 3 for our y-intercept. Fairly simple concept. Now, that's the equation of the line. So I mentioned kind of when we see it, we see y is equal to negative 2x plus 3, because that's the equation of the line. We would leave y and x alone. But what that means is that really is describing all of the points on the line. So we can use, or we can see if points are on the line, or we can use that formula and test to find other points on the line, or test to see if the points actually exist on the line. So let's say we have this point 0, negative 3. To test to see if that's on the line, I'm going to pull that equation down, y is equal to negative 2x plus 3, and I'm going to test my solution. I'm going to test 0, negative 3. I'll plug that into the equation. And 0 times negative 2 is 0, so that leaves me with 3 on the right side and negative 3 on the left side. So those two sides are not equal, so that answer just should not check out. Or since we're talking about lines, 0, negative 3 is not on the line. Let's see another point, 1, 1. Plug that into both sides. Y is 1, x is 1. Negative 2 times 1 is negative 2, and negative 2 plus 3 is 1. So 1, 1 is indeed on the line, since 1 is equal to 1. One more time, negative 2, 7. I plug in 7 for y. I plug in negative 2 for my x. Negative 2 times negative 2 is 4. And 4 plus 3 is 7, so negative 2, 7 is on the line. So these are actually like individual tests. We're not testing for slope or average rate of change or linearity or anything like that. We're just taking this equation, y is equal to negative 2x plus 3, and we're plugging in points to see if that's actually on that equation of a line. Okay, last bit of information. Example 5 says, write the equation of a line with the slope negative 1/3 and the intercept is 0, 8. Well, I know my equation is y is equal to mx plus b. My slope is negative 1/3. My b is 8, so I just plug those into the equation. I'm left with y is equal to negative 1/3 x plus 8. And again, that's kind of what the equation should look like. Okay, so let's dive right into the slope-intercept application. So let's say we have a question. In 2005, a ranch had 12,000 cattle. Projections predict the ranch will lose 2,000 cattle per year. Write a symbolic rule to find the amount of cattle over T years in thousands. And I want to emphasize that word thousands. So this symbolic rule is going to look a little bit funky because we had thousands in the beginning. But if I'm writing a symbolic rule, I'm not going to write 12,000 and 2,000. I'm going to write 12 and 2, because that means that I started out with 12,000 cattle and I'm losing 2,000 cattle per year. So that's where that 12 minus 2t comes from. If I wasn't asking for it in thousands, yes, you could argue that it should be 12,000 minus 2,000t, but it's really just simplicity's sake and graphing sake. It makes it a lot nicer if we just change it into that. So be aware of that when we're going through the rest of this problem. That comes from, again, the base is 12. We started with 12,000 cattle and we lost 2,000 cattle per year. Easily enough, the next question asks, what's C of 5? Well, we know C of 5 is evaluating, so we plug in 5 into our formula. And again, that's not C times 5, that's just meaning that we're evaluating it at 5. And then 2 times 5 is 10, 12 minus 10 leaves me with 2. So that C of 5 is equal to 2, but then the next question is very valuable. What does it mean in the context of the problem? Well, if that is 5, that means 5 years after the start. So we started in 2005. That means 5 years past that will be 2010. And that 2 stands for the fact that that's our output, how many cattle we have left. So in 2010, which is 5 years after the start, there should be 2,000 cattle. Follow-up question, when will there be 6,000 cattle, and what will this look like as an ordered pair? So before we were evaluating, we were plugging in 5 for our time, years, and finding what the amount of cattle left is. Here we're given that there's 6,000 cattle, so that's our output. So I'm going to change my equation, or I'm going to plug in 6 for my amount of cattle. Then I'm going to go ahead and solve for my t. So I'm going to subtract 12 from both sides. Leaving me with negative 6 is equal to negative 2t. Go ahead and divide both sides by negative 2. And I get 3. So this question's not asking what does this mean in the context of the problem. It's simply asking what does it look like as an ordered pair. And this goes back to the very beginning of graphing. An ordered pair is a point. So this as a point is my output is 6, my input is 3, so it would be 3 comma output is 6,000, yeah, 3 comma 6. And then to answer the initial question, sorry, the beginning part of C actually was asking when will there be 6,000 cattle. So I solve for my t is 3, and that's 3 years past the beginning. So we go back to the initial 2005 plus 3 is equal to 2008. So in 2008, there will be 6,000 cattle. But then again, if I want to write that as an ordered pair, it's simply 3 comma my output 6. Sorry for that confusion. So this is going to keep building on that same equation. So it's continued because example 1D is using that formula that we talked about in part, I believe, even part A is when we developed this formula. So the cost is 12 minus 2t. We want to plot it using slope-intercept form. Well, we know that so y equals mx plus b. It's a little bit tricky because it's not mx plus b in this case, but m is always what's next to our variable. So our m is negative 2. And again, if we want to write that as a fraction so we can actually use it to plot, that's negative 2 over 1, since it's the whole number. And then the y-intercept is what's left, it's that b part. So even though the order is flipped, the really important thing is the slope is next to our variable, and the intercepts are constant, which is not next to the variable. And from that information, we can go ahead and graph. So I'm going to put in my titles, cow population, years, and cattle in thousands. And I should label the size of the graph, but I'm actually going to go up by increments of 1. And so if it's not explicitly stated, that's what it's assumed to be. So I don't actually have to label it if I'm making it every tick mark mean 1 unit. I plotted my y-intercept 0, 12. That's at the very top left of the graph. And now we're going to kind of see what I was talking about initially with plotting. Is if I want to use my slope to build my graph, that's rise over run. So my rise is negative 2, meaning I'll go down 2. My run is 1, so I'll go over 1. And then that's where my next point goes, so I plot a point there. Now I can go ahead and repeat this. Rise down 2, over 1, and that's my third point. And then from there, that's actually all I need to form my line. Sorry about that. And now I draw a line that goes through all 3 of those points. Question E says, identify the third point we plotted and interpret its meaning. Well, looking back at the graph, my first point was my intercept, then I had my second point. The third point was the third one I plotted. So then if I'm looking at it on the graph, 1, 2 over 2, horizontal is 2, up 8, and there it is. There's my third point, 2, 8. Now, to interpret its meaning, the 2, again, is how many years past 2005. So 2 years after 2005 is 2007, and then the 8 is the output, how many cattle I have left in thousands, so it's 8,000 cattle. Use the slope to determine the change in cattle over any span of 4 years. And what this is asking us to do is go back to that very first slope application problem that we went through and actually set up a proportion. So again, my slope is, I'm going to bring it over, -2/1, and that -2 is the amount of cattle I'm losing, that's the top, over the years that passed. So if I'm going to set up my proportion, the bottom right of my proportion, so that's the change in cattle over the change in time, again, a very fancy way of writing it, once it shows up, delta. And now I'm going to set up my proportion. As I mentioned, the change in time is 4 years, and I'm going to find the change in cattle over that 4-year span by, once I have this proportion set up, it's easy enough to do a quick cross multiplication. 4 times -2 is -8. X is 1 times X is X, and that's all I have to do. I don't have to go any additional problem solving. And then to answer the question, every 4 years, there should be a decrease of 8,000 cattle, because that's my change. My change in time is 4 years. My change in cattle is 8,000. And specifically, it's a negative change. Okay, last slide of this very lengthy first problem. Example 1, part G says, use the result from part F to determine the amount of cattle in 2009. So let's go back to that. What did it say in part F? Okay, well, we set up our proportion. We found out that every 4 years there should be a decrease of 8,000 cattle. And in this question, it says how many cattle there should be in 2009. Well, that's conveniently enough 4 years after my starting point. So to bring that over again, every 4 years, oh wait, there we go. Every 4 years there should be a decrease of 8,000 cattle. Well, since it's 4 years after my starting point, and I started out with 10,000 cattle, you may have already figured it out. Sorry, I didn't have 10,000 cattle in the beginning. I had 12,000. So I had 12,000 cattle in 2005. That's 4 years past, and now we're talking 2009 is 4 years past my starting point. So I should have 8,000 less cattle. Well, 12,000 minus 8,000 leaves me with 4,000, and since we have that test coming up, that should say 4,000 cattle. If you're doing an applied problem, there should be some sort of units tied to the answer. So I would not be getting full credit on this question. Oh, now I will be. In 2009, there should be 4,000 cattle.